In chapter 2.1, we're going to talk about limits and their properties. This is really for us kind of the real true beginning to the class where we're going to start to work with new material. And in section 2.1, we just kind of give an overall brief preview of what calculus is all about. To kind of put things simply, if you think about all of the mathematics that you've learned up until this point, so things like, whether it's a bunch of algebra classes or geometry or even trigonometry, those all kind of get lumped under the term what we call pre-calculus. And there's a lot of things we can do with pre-calculus. We can find areas of rectangles, polygons, we can find average rates of change, etc. Once we introduce in this chapter the thing called the limit process, what that is going to enable us to do is to kind of push our pre-calculus concepts even further. And with the combination of the stuff we've learned before, with this limit process, that's what's going to take us into calculus. Okay. And there's so much stuff that you can do, with calculus that we wouldn't be able to do without. For example, when we were to find the value of f of x when x equals to c, we know how to find function values by plugging in. It turns out that maybe a function doesn't have a value at c, but what we'll be able to do with calculus is we can actually find the limit as x approaches c of the function to see how things are behaving. Without calculus, we can at least find the slope of a straight line. So one of the things we know is that on a line, the slope between any 2 points is the same, and that's your old school y2 minus y1 divided by x2 minus x1 formula. With calculus, we can actually talk about the slope of a curve at any point. And one of the things that you notice is that, if you think about being on this curve, if there was like a roller coaster, if you're able to ride this thing, the steepness or the slope changes depending upon what point you're at. It's not a constant slope. So that's something we'll be able to do with calculus that we weren't able to before. Some of the other things that we were able to do, things like secant lines, average rates of change. We will now be able to find the equation and slopes of a tangent line to a curve at a point, as well as the instantaneous rate of change at a particular instance of time. It's well known, although it might not be well known to us, but we could calculate the curvature of a circle, kind of how rounded it is. It's actually 1 over the radius. Whereas now we can talk about the curvature of a curve, which is kind of how bendy the curve is at different points. So there's a lot of things that we're going to be able to do now once we add the limit process to our knowledge that will allow us to solve some pretty cool problems. And we will focus on the majority of these this summer, or I should say this semester. So those are some things we could do with differential calculus. The second half of calculus is what's referred to as integral calculus, and that'll allow us to do the following types of generalizations. One thing we already know how to do is how to find the area of a rectangle. Now we'll be able to find the area of some really kind of weird-looking regions that reside under curves. From basic physics, we know how to calculate work done by a force. If you have a constant force, work is just force through a distance. Now with integral calculus, we'll be able to find the work done by a variable force. In addition, we can find things like the centroids, or the center of masses of some odd shapes. We can find how long curves are, and we can also find surface areas and volumes of three-dimensional shapes, whether they're from resolution, surface of resolution, or just general slices and things, as well as find the sum of an infinite number of terms. So there's a lot of really cool stuff we're going to be able to do as a result of doing calculus in this class. The first one that we're going to start with is kind of an introduction, is that of the tangent line problem. Okay, so if we were to ask you what is the slope of this tangent line to the curve y equals f of x at the point P. So here we have one point. This is what we mean by a tangent line. It's a line that touches the curve at exactly 1 point. If we were to try to calculate slope, well, the one thing we have for slope is our old school y2 minus y1 divided by x2 minus x1 formula from pre-calc. The issue with trying to use this formula in this setting is we don't have 2 points. We don't have a pair of ordered pairs. We have just a single point, the point P. So the fundamental concept of calculus kind of works like this. It says, okay, here's what I know. I know how to do this. Now this is what I want. The question is, how can we bridge the gap between something that we already know how to do and something that we're currently not able to do? And that's where this limit process is going to come in. So let's suppose that we're really focused on, and this is really what we want. We want to find the slope of this tangent line to the curve at the point P. So we want the slope of the tangent line. So we say to ourselves, well, I can only find slope if I have 2 points. So here's the idea. Let's go off of the x-axis. Let's go to the right a smidge, and that smidge we're going to call delta x. So I'm going to add delta x, a small amount to my x value, just to kind of get a second point that's going to be on the graph. So now we have a second point. I take that first value, I guess they call it c here in this context. So here's c plus delta x. And now I do have 2 points. We have the second point that's located at c plus delta x, and whose height would be given by the function evaluated at c plus delta x. And then we have our original point, which is the point of tangency that we're hoping to get, which is at the ordered pair c comma f of c. With those 2 points, I can calculate the slope of the line that passes between them. That's the slope of the secant line. And here's what we would get. It would be y2, that's f of c plus delta x, minus y1, that's f of c, all divided by x2, which is this thing, c plus delta x, minus x1, which is c. In the denominator, the positive c and the negative c cancel, and what we're left with is this expression here. We saw this during the review, but that is what we call the difference quotient, and this is where it comes from. Visually, what it graphically represents is the slope of the secant line to the function f that passes through the points c comma f of c, and a second point c plus delta x comma f of c plus delta x. So this is something we can do, because now we have 2 points, we can compute that slope. And now here's the limiting process idea. What happens if we keep adding less and less and less each time? So here's that second point, c plus delta x. What happens when we let delta x go to 0? Well, if we're adding less and less to c each time, then the points that are on our second point that's on our curve, those secant lines, as delta x gets smaller, those secant lines are going to approach and get closer and closer and closer to approximating our tangent line. So much so that the approximation will become exact if we're able to take a limit as delta x goes to 0. So pretty clever. We say, okay, I want this new thing. I'm not able to do it with what I currently know. So you take a step back and say, well, what can we do? We do the slope between 2 points, and then you let that second point approach the first point in the limit, and then the sequence of those slopes of the secant lines will approach the slope of our tangent line. So that's kind of an example of how we're going to be using calculus to find slopes of tangent lines. A second type of problem that we'll come back to later on in the class is going to be the area problem. Suppose we asked you to find the area of kind of like this funky, irregular shape, which is under the curve y equals to f of x. So we look at it and we say, okay, it's not a circle, it's not a triangle, or it's not a well-known shape that we would have a direct formula for this thing. So once again, we think to ourselves, okay, I can't find the area of the shape directly, but you can ask yourself, what things can we find the area of? And the answer is, one of the things that we're very good at finding the area of is rectangles. So let's kind of inscribe or kind of stick under the curve a bunch of rectangles like this. And at least if we calculate the area of those rectangles, which is something we're able to do using 1, 2, 3, 4 rectangles, we'll at least kind of get a ballpark or an estimate for what the area under the curve would be. Again, it's not going to be exact because we're kind of missing some parts out, and we might have a little bit extra in other places, but at least it gives us something to kind of do as an estimate. And one of the things we notice is if I go from, like, let's say using 4 rectangles to, let's say, maybe using more. If I go 1, 2, 3, 4, 5, 6, 7, 8. If I put 8 rectangles under the curve, then one of the things that we notice is that the approximation becomes better. We're kind of able to kind of hug and fit the curve a little bit more, so we're not kind of missing out on as much area, nor are we overestimating and adding too much extra area via some of these rectangles. And so the idea is, well, okay, if I add more rectangles, if the approximation gets better, instead of using 8 rectangles, let's use 100 rectangles. Or let's use 1,000. Or let's let the number of rectangles we use approach infinity. If we do that, the better and better our approximation is, so much so that if we pass to the limit, we will actually be able to find the exact area of the region under this curve. And this is an example of what we'll be doing with integral calculus. So lots of cool stuff we're going to be able to do once we're able to kind of add in this limit process. And what we'll be doing is spending the rest of Chapter 2 kind of understanding what it is, how it works, and then we'll be able to hit the ground running in the class.